Okay, continuing on. In the next set of problems, well, term by term differentiation and integration, that seems to be simple if you're looking at the terms themselves. But what we want to generate a method of taking a derivative of the power series as it is. Again, you're going to be using those power series. Those power series are really what you program a calculator to approximate an irrational number, to figure out certain values, computers, blah, 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 all of these different things. So let me start you off really simple. And the idea is fairly simple because we know how to take a derivative if they're in this form, or integrate if they are in this form. Well, term by term is simple. Suppose that a power series looks like this. This is a power series centered at x equal a. This converges. Don't pay attention to that part. None of that part. That's not a big deal. That's really easy to find. But here's the deal. If f of x is given to be this power series, which is a constant, let you n equals 0, if you take a derivative of that, then the derivative of this will be a 0. That's gone. Derivative of this will be c sub 1. Derivative of this will be c sub 2. Bring the power down, subtract 1 from the power. Bring the power down, subtract 1 from the power. You get that term. So notice I had c sub 0 plus c sub 1 x minus a to the 1 plus c sub 2 x minus a squared. The list goes on. When I took a derivative, and that's why I always suggest if you're given a series, list the first 3 terms just to know when I take a derivative, I lost a term. If I lose a term, I have to reflect that in the summation. If I want to write this as a summation, I notice that I can no longer start at 0 because I lost that one term. So now I'm going to start with 1, and that's why you really boost this one up. Now, if you want to integrate, well, the same analogy applies. If you want to integrate c sub 0 plus c sub 1 x minus a to the 1 plus c sub 2 x minus a squared, well, if you integrate this, first you're going to get a constant. This is going to be c sub 0 x. This is going to be c sub 1 x minus a. Add 1 to the power, divide by that. This is going to be c sub 3 x minus a cubed. Add 1 to the power, divide by that. And the list goes on. And that's how they got this. Well, altogether, that's c sub 0 plus c sub 1. Again, we're basing everything off of this. We're going to get a constant, the constant of integration, plus c sub n. We take the variable part. We simply add 1 to the power, divide by that. And everything remains the same. And that's pretty much it. So yes, term by term, it's easy to do. But we want to really do it using power series. And here we're going to do both until we get the hang of this. So when I look at this, the first thing I should do, I should say, look, f is actually, let x equal, n equals 0. X to the 0 is 1. N equal 1, 2, the list goes on. Now, we know this is true. We know that, hey, that's a 1, that's a 1, that's a minus. I take x squared raised to the n power, I get this piece. No problem there. It says differentiate the series. They want us to do the left and the right. Well, look at the left. The derivative of the left, this is simply 1 minus x squared to the negative 1. Bring the power down, subtract 1 from the power. So that is 2x divided by 1 minus x squared squared. The power series here, if I take a derivative, do you see that I lose a term? So since I lose a term, I have to boost this 1 up. And all what I do is pretty much what I've always known. Oh, I didn't mention that when we talked to you about the series here. All what I did here was I brought the power down and subtracted 1 from the power. And that's how we're going to take a derivative of the power series. We're going to say, look, bring the 2n down and subtract 1 from the power. Now, here's the deal. If you can make that x to the n power, you must. If not, You could leave the answer like that. That's not a big deal. I could say, look, I'm going to make that a 0. So shifting this one down, the catch, you have to adjust all of these ends up. That will be n plus 1 x. And if you replace this by n plus 1 minus 1, that will be 2n plus 2 minus 1. That's 2n plus 1. Both of those are the same. There is no need for you to go from this form to this form. The only time you have to do that, if you could make that x to the n power. You could only do that if it's shifted left or right, not if it is compressed or stretched. So multiplying the n by a number, you can't fix that. And that's pretty much all there is to it. So both of those are saying the same thing. Now we look at another problem. We say, okay, well, now they want us to integrate. They're given series term by term from 0 to x. Okay, obtain the corresponding function. Here we are. So if I'm given this, I'm going to integrate each of those. Well, let's see how this works. Integration doesn't really have any flaws or something to be careful with. This is the integral from 0 to x. That's what they said to do, of 2x over, actually I could do it here. If I run this 0 to x, let's see what happens. I'm gonna let u equal 1 plus x squared, and du is 2x dx. So that's simply the integral of du over u. I know what that is. That is simply natural log of absolute value of u. And what was u? u was 1 plus x squared. And here, what's that integral with respect to x? The 2 you leave alone. C plus 0 to infinity. The constant you leave alone. The only piece you have to worry about is the varying part. Add 1 to the power. Divide by that. So this is what I'm getting. Natural log of 1 plus x squared, I don't need absolute value because this is always positive, is c plus, if I factor a 2 out of this, wouldn't these two cancel out? That is the series n equals 0 to infinity, negative 1 to the n, x to the 2n plus 2, divided by n plus 1. Actually, I'm going to factor a 2 out of that and make it n plus 1 as well. And pretty much I just figured out a form for this. Now, since I have them equal, I could let x equal 0, then natural log of 1 equals c. The only way you can get this series to 0 out if you put a 0 in there. And we know natural log of 1 is 0, so c equals 0. So we know that natural log of 1 plus x squared equals the series n equals 0 to infinity, negative 1 to the n over n plus 1, x to the 2 into n plus 1, or x to the 2n plus 2. It makes no difference. And there it is. That is my power series for natural log of 1 plus x squared. Notice that I just found a power series for something that doesn't look like 1 over 1 plus x squared. Recall this again. Now we're going to use that. Now this is how we really use this. We say, look, I want to find a power series centered at x equals 0. Okay, well, I don't know how to find a power series for a natural log. Let this be f of x. Let natural log of 1 minus x equal f of x. Well, if I take a derivative, what's the derivative of this? Isn't that 1 over 1 minus x times a negative 1? Isn't that negative the series n equals 0 to infinity of x to the n? Isn't that true? Then, how are those related? Natural log of 1 minus x squared equals f of x, and f of x is the integral of this with respect to x, and that's the integral of this with respect to x. So natural log of 1 minus x squared equals negative the series equals c minus the series n equals 0 to infinity x to the add 1 to the power divide by that. Well, I can fix that. I could say, look, natural log of 1 minus x is c minus the series. Since I can make that x to the n power, and how do I do that? I shift that 1 down. This shift 1 down, that becomes n. To adjust, this has to shift 1 up. And if you're not certain what I'm doing, plug n equals 0 in there and plug n equal 1 in there. You should get the same terms. Now, since I have natural log equal, I could figure out what c is. I'm almost done. If I let x equal 0, natural log of 1 equals c minus, if you put a 0 there, that's the only way that series will be 0. Adding an infinite amount of zeros is 0. So I know that this is 0. So a power series representation for natural log of 1 minus x, I can write as a series n equal 1 to infinity. Did I miss a negative out of that? Let me see. There was a negative 1, negative 1, negative 1, negative 1. No. Again, a sub n x to the n. You always want to write it that way. And this is from n equal 1 to infinity. And there it is. Okay, that's how we're going to find power series for any natural log. We're going to take a derivative of it, make it look like one of those, use that fact, and then integrate the series and figure that out. Similarly, if I want to figure out a power series for 1 over 1 minus x squared, I don't know how to do that. But I know that if you take a derivative of 1 over 1 minus x, if you take a derivative of that, you pick a 1 over 1 minus x squared and you proceed that way. And that's how we're going to find for anything that could look like this. And here's another example. Why is this far around it? Okay, it doesn't matter. Now what? Looking at this problem, the same deal comes up here. We would like to figure out what the power series representation for this is. Well, we only know of one technique. This is what we do. We say, look, let's start with 1 over 1 minus x squared. 1 minus 1 over x squared, because I know the derivative of that is going to give me that squared. Again, if I have x to the negative 2, if I have x to the negative 1, and if I take a derivative of that, I know the derivative of that will be 1 over x squared. So to square a denominator, I'll say, look, I know what this is. This is the series n equal 0 to infinity of x squared to the n. This is the series n equals 0 to infinity of x to the 2n. And I'm aware if you let n equal 0, you're getting 1 plus x squared plus x to the 4th. Okay, now if I take a derivative of this and a derivative of this would be, so this is, I'm going to erase this, 1 minus x squared to the negative 1. Bring the power down, subtract 1 from the power. That is positive 2 over two x over 1 minus x squared squared. Okay, and what's the derivative of this? Well, you're going to lose a term. If this is f, f prime will be 0 plus 2x plus 4x cubed, and the list goes on. So that's going to be the series n equal 1 to infinity. Bring the power down, subtract 1 from the power. And basically, you're done right there because there's no way you could fix that. Well, if that's the case, that's a fine answer. If you look at the back of the book, they might in the back of the book say, look, this is the series. They might shift this 1 down. You don't have to. By doing that, you have to shift those one up. That's 2 into n plus 1 x. And just be careful when you adjust this power, you're going to replace the n by 1, not the whole power. So that's really 2n plus 2 minus 1. That becomes 2n plus 1. And there it is. Either of those answers is fine. If the back of the book has one over the other and you got the other case, it doesn't really matter. You really don't have to match it that much. One to go. I'd like to find the power series for natural log of 1 plus x squared. I don't know how to do that. Well, this is what I'm going to do. I'm going to take a derivative because I know the derivative of natural log of x, if f equal natural log of x, I know the derivative is 1 over x, and I could write this with ease as a power series representation, right? I could say that's 1 over x minus 1 plus 1, 1 over 1 minus 1 minus x, and write this as a power series and go on. The derivative of natural log of x is 1 over 1 plus x squared times 2x. And I know this is 2x times 1 over 1 minus negative x squared. So I'm not skipping any steps in this case, and I'm writing this on one line so you could see it. The series n equals 0 to infinity, and I'm going to replace the negative x squared to the n power. So now I have a representation for f prime, which is 2x the series n equals 0 to infinity, negative 1 to the n power x to the 2n, and if I combine those, I'm really looking at this series. Negative 1 to the n power times 2 times x to the 2n plus 1. When you multiply like terms, you combine the powers. Now I say, look, natural log of 1 plus x squared, which is f, and those are connected by integrating this with respect to x, and that gives me a power series representation of natural log of x. That's how my calculator approximate a log of any value that is irrational. That's how they do trig. That's how, trig is going to come up in the next section, sine, cosine, tangent, all of these things. Well, this is going to be c plus the series n equals 0 to infinity, negative 1 to the n power 2, add 1 to the power, that's 2n plus 2, divide by that. And if I factor a 2 out, I notice that those two cancel out. Not only that, that is c plus the series n equals 0 to infinity, negative 1 to the n, x to the 2 into n plus 1 over n plus 1. Now, since I have, if I put a 0 in there, I know that's a 0. And if I put a 0 in there, that's natural log of 1. That means c is 0. So my final conclusion is that my power series for natural log of 1 plus x squared would be the series n equals 0 to infinity, negative 1 to the n over n plus 1, x. Either you write 2n plus 2 or factor that. And again, one is not preferred over the other. Both of those are saying the same exact thing. And you might notice that the author did this. They shifted this one down. You don't have to do that. Again, you only do that if you could make it x to the n power. So if it's shifted, you could fix the shift. But if it's stretched or compressed, there's no way of doing that. Shift this one down, this one down. So that is n negative 1, n minus 1 or plus 1. The author seems to like the n plus 1 more, but it doesn't matter. They both alternate. If you degraded that by 1, you really want to compensate by increasing this n by 1 so that the first term of this term and this term match. And there's your final answer, and that concludes this section.